The topic we are going to discuss about is a 555 timer. This comes under the unit 4 of our syllabus. So this 555 timer is a highly stable device used for generating an accurate time delay. So the main thing, we are going to calculate the time delay using this 555 timer. So this 555 timer was first introduced by the Synergetics Corporation, and they designated the 555 timer as NE555 or ACE555. So this is the main thing we have gone for. This 555 timer is for the calculation of the accurate time delay, and this 555 timer, it ranges in the time delay from microseconds to hours. And the 555 timer, the supply voltage we used is the plus 5 volt to maximum of plus 18 volt, and which drives the load to up to a 200 milliamps range. Okay, so in this where we can use this 555 timer. So this 555 timer can be used in pulse generator and a ramp generator, and mainly used in the oscillators, and mono-short. It's like a monostable, we can call it as mono-short vibrators, multi-vibrators. So these are the applications of the 555 timer. So the main thing we use for the time delay calculations. So coming to the pin diagram of the 555 timer. So this Synergetics Corporation has introduced this 555 in terms of 8-pin dual inline package or the 14-pin dual inline package. So in this, the 8-pin we have designated as, the first pin represents the ground terminal, and the second pin is for the trigger pulse. The third pin we are going to take the output, and the fourth pin we are going to reset, and the fifth pin we are going to apply the control voltage. The sixth pin is for threshold, and the seventh pin is for discharge, and the eighth pin is for supply. So here the supply VCC is given, and the first terminal is for grounding. We are applying a pulse like positive pulse, trigger pulse, or the negative trigger pulse is applied to that the pin terminal 2, and the reset, it's like a flip-flop conditions or in terms of counter. So here, for example, the 556 timer, this is also a one kind of timer. It has a 555 timer inbuilt, and we have a counters. So in this counter, we can take a, here when this 555 timer, the time delay ranging is from microseconds to hours, where in case of this, it's like an hours to an days. So in this counter is like a programmable built-in counter is built inside this 555, it's 556 counter. This 555 plus this counters are included in this 556 timer. And this counter concepts, we can make everything to be cleared at the end of the operation. So we can make our value to reset as 0000 for the 4-bit counters. Then control voltage VC is applied, and we can compare with the threshold voltage. Then if we have used a capacitor concepts, we can store and discharge the voltages, and the VCC supply is given. This is the pin diagram of the 555 timer. This is the resemblance. This is like a functional diagram of this 555 timer. So initially we start, what are the components present in this circuit. So initially we have an UC is an upper comparator, and LC is a lower comparator. Then we have a flip-flop. That flip-flop is like SR flip-flop, Here the R is given from that upper comparator output is given to the R terminal, and the lower comparator output is given to the S terminal. This S and R represents the set and reset conditions. The output is for the flip-flops are Q and Q bar, and we have a reset terminal that is connected to the Q2 transistor, and the output of this Q2 transistor is given to both the power amplifier. This is nothing but it acts as an inverter, and this makes as the input to that Q1 transistor. Here we have the main thing. We have a 5 kilo ohm resistors, 3 5 kilo ohm resistors. First I'll draw with 3 5 kilo ohm resistors are used as the internal resistor, acts as a voltage divider. Okay, so which acts as a voltage divider, and it provides the bias voltage of 2/3 VCC and 1/3 VCC. So this 2/3 VCC is given to the upper comparator, and 1/3 VCC, here I have to write a 1/3 VCC is connected to that lower comparator, and we are going to make up with this trigger voltage. This is nothing but the 1/3 VCC. In between the voltage we have 2/3 VCC. Here it is 1/3 VCC that is applied to that lower comparator. So this is the first thing. We have 5 kilo ohms of 3 things acts as the voltage divider, and it is connected to the 2/3 VCC of VCC is connected to upper comparator, 1/3 VCC is connected to lower comparator, and VCC is the supply voltage. Okay, so this is the thing we have given to the upper and lower comparator. Based on these two voltages, fix the necessary comparator. So in this upper comparator or the lower comparator, based on this requirements, it fixes the necessary comparator threshold voltage, and they help in determining the time interval T. Okay, so it helps. Based on this upper and lower, we have a threshold on the trigger pulses. Based on this, we are going to define the determining the time interval factor. So in this, initially we should know the concept of that comparator. As I mentioned, A is equal to B and A greater than B or A less than B, and keeping this B as the reference voltage and A as the input voltage. Here the supply voltage, as is mentioned, based on the spin diagram, I am going to explain this functional block diagram. So here the 8th pin is VCC. So the 8th pin supply VCC is given, which is the 3 kilo ohms, and the first pin is to be grounded. Okay, then the second pin, the input we are going to give is 1/3 VCC. Sorry. Yes, this is the 0 volt, and 1/3 VCC is charged from this side. So 1/3 VCC of that negative pulse triggered is given to that lower comparator, and then we are going to take the output at the 3rd pin. Then 4th pin, we have a reset connection that is connected to the transistor Q2. This transistor Q2 has an inbuilt reference voltages, and the output is given to the input of your transistor Q1 and to the power amplifier. So whatever may be that output which is converted, that is to be inverted as an output using that power amplifier, and it is processed to the output to pin 3. Then we have a control voltage, then we have a threshold voltage. We will be fixing certain voltage, and we have a discharge in the capacitor Q1, transistor Q1, which discharges through the 7th pin. These are the terminals in the 555 timer are used in that functional diagram I have been explained. So based on this, the first concept in the standby mode, as in the steady state or the stable state. Okay, so in that stable state condition, we have the flip-flop. This flip-flop will be, that Q bar will be in the high condition. So in that means that your Q bar value will be 1. So whenever this flip-flop gets on, that time your R equal to 1, your Q will be a 0, that Q bar will be 1. In the set condition, your Q will become 1 and Q bar will become 0. That is the condition when we use in case of your digital logic circuits as an SR flip-flop that can be designed either using a NAND gate or using a NOR gate. So in that condition, whenever that set condition occurs, that output of your Q will be 1 and the complement of Q is 0. So initially in that stable state, I have made my Q bar as 1. So in the stable state, that Q bar as 1, which makes my output. This Q bar is given here. Now it is given to the Q1 transistor. Now we are going to consider only about the output part. So my input is 1. What will be the output? So now this acts as an NOT gate. You should have a bubble in that. So when one input is given, you should get an output as 0. That means your output will be in a low condition. It acts as an inverter, then it produces an output as low condition. So in that condition, the second time, when we apply a negative pulse, when we apply a negative trigger pulse to that pin 2. So in that condition, the 1/3 VCC is greater than the lower threshold level, then it makes your comparator to on. So here it is defined that 1/3 VCC and you are applying the pin negative trigger pulse. So it's like a minus 1/3 VCC is lower, then it makes your flip-flop terminal with the S condition. That is, whenever your condition negative pulse is applied, it gives your set condition. Your condition is set, you are making your flip-flop to on. In that condition, your Q is 0 and Q is 1 and your Q bar becomes 0. So in that condition, it becomes 0. In the second condition, Q bar becomes 0. So now it becomes 0. The output of your inverter is 1. So the output will be in a high condition. Okay. So when we apply a positive excursion at the threshold voltage, so here we are applying a threshold voltage of positive pulse to that pin terminal 6. So it passes through the 2/3 VCC and it gives the output of that upper comparator to high, and it makes your reset terminal of this control flip-flop gets worked high. So in that condition, you are applying a positive at the upper comparator, then it makes your reset terminal. So in that reset condition, your Q becomes 0 and your Q bar becomes 1. So ultimately your Q bar becomes 1, then the output will become 0. Your output will be low. So this is the operation of the functional diagram of this 555 timer. So the thing it has, so the 555 timer have 8 pins. So in that main thing we are going to discuss that pin as 8th pin is a supply pin and the 3rd pin is the output pin. So it's like an input is supply voltage and the output is our 3rd pin. So here we have the 8th pin supply is with the 3 resistors. That 3 resistors with acts as the voltage divider. Internal resistors acts as the voltage divider, and it is connected to that upper comparator and that lower comparator. So this output of these two comparators is connected to that control flip-flop. So this control flip-flop output has two outputs. The one is the Q and the other one is the complement of Q. That complement of Q output is connected to that Q2 transistor, and here the reset pin is given to the transistor terminal Q2, and the output of this Q bar is given to that inverter, and it is taken as the output. So it may drives the Q1 transistor with the discharge connected to the discharge pin, whereas the other terminal is to be grounded. So here we should know the basic concepts of that comparator. By keeping the reference voltage, when we apply an input voltage, if we get an input voltage is greater than the reference voltage or it is less than the reference voltage. So here we have initially, when we are discussing about the functional diagram of the 555 timer, we have a control flip-flop. In this control flip-flop in the steady state, that means in the standby state, it's a stable state condition. We have a Q bar output as 1 and Q as the 0. So once in this condition, the Q bar as 1, so I am going to apply this to that power amplifier. This is nothing but an inverter. If I give an input as 1, we will be getting an output as 0. So in that condition, when we apply a negative pulse to the terminal pin, the second pin is for triggering, so I am applying a negative pulse triggering to that lower comparator. So we already have an 1/3 VCC to that lower comparator is applied. So it is given, then we will make comparing these two voltages. Once it is the lower comparator is high, then it makes this flip-flop with the set condition. So once the condition is set, we can make my Q as 1 and Q bar as 0. So this Q bar of 0 is connected to the inverter as an input. So 0, the output of this inverter will produces 1, it will be in the high state. The other condition, to make my upper comparator to say my value as high, then I can give a positive value of the threshold, that is to be compared with the 2/3 VCC. So in that condition, if the upper comparator gets satisfied, the voltage, it makes my condition to be reset. So in that reset condition, I will be making my Q as 0 and Q bar as 1. So again this 1 is applied to that inverter, will be getting an output as the low output. That is the condition behind this. So far we have discussed the 8th pin, 6th pin, 5th pin, 2nd pin and this. So that coming to the reset condition. So in this reset condition, what's the use of that resetter? So this reset input provides the mechanism to reset the flip-flop. This is the condition we are going to give that reset pin, which makes this thing to do this Q bar to reset, which overrides the effect of any instructions to coming into the flip-flop. So in this condition from the lower comparators, right? So in this condition we are applying a reset pin. This reset pin will trigger this Q bar, and this works with the help of that lower comparator. So in this condition, which we should not get, it should gets overridden, and it should not get overridden all the time. So we have to make when the thing to be overridden. So the reset voltage to be overridden only if the value should be less than 0.4 volt. If in case if it is beyond that, so it is given directly to that VCC supply voltage. If it is less than 0.4 voltage, that too from the lower comparator part, we can override the effect of that resetter into that lower comparator side. If not, if the reset is not used, it is returned to that VCC. So here the Q2 serves as a buffer. So here the Q2 serves as the buffer. It's like a temporary storage, and the input of that internal voltages V reference is driven, and it has a supply voltage obtained from the supply voltage VCC. So that is the thing, it is driven by the internal voltage Vref. So this is the concept of this 555 timer. Coming to that concept of monostable operation. So in this condition, again the first terminal represents the ground terminal. The second terminal is for the trigger, the 8th is for the supply, and the 4th is again, as I said, the Vref is connected to the voltage terminal. If the reset value will be less than that 0.4, it may be overridden. And the thing, if it is reset concept is not used, then you can connect that internal voltage, reference voltage is connected to that VCC, the same as VCC is connected to the 4th terminal and the 8th terminal. So here the 7th and 6th terminal is connected with the input resistance R and the capacitance C. Then we have taken an output at the 3rd terminal. Here the between the 1st terminal and the 5th terminal as the control voltage is connected with the capacitor with a 0.1 microfarad. The same diagram of the monostable operation is given in terms of this. Again we have a 5 kilo ohm resistors with the 2/3 VCCs connected to upper comparator, 1/3 VCCs connected to the lower comparator, and we have a flip-flop concept. Then the reset pin is given to that Q2 transistor, which acts as a buffer, and it is connected to the power amplifier, which is an inverter, basically an inverter, right? Then output of this Q2 is connected to the input of Q1, which is met with the discharge pin. So here the capacitor is used, and the first terminal of this is to be grounded. Then we apply the trigger pulse to the lower comparator. Here the control voltage VC is applied to that upper comparator, and the 6th pin threshold is given to the upper comparator. The only difference in this and this diagram, here we have that one pin and it is connected to the capacitor. Yeah, see the 7th and 6th pin of R and C. So this R and C is connected between the 7 and 6th pin. Okay, so this is the pin diagram of that monostable operations. So in this, again it starts with the standby state. So it's like a stable state. Initially in that standby state, the flip-flop Q1. So here I am going to discuss about the transistors of Q1 and Q2, when it will be in on condition, and how will be the output of that based on this power amplifier. So in that standby state, your Q1 transistor will be on. The flip-flop makes my Q1 transistor to be on, and the clamping the external timing resistor, this capacitor, external timing capacitor C, to be grounded, So here that output remains. So once we are making my transistor to on, so this will be in on one condition. The one is passed to that inverter, it gives an output of 0. So in that condition, we are making the external timing capacitor to be grounded and the output to be low condition. So in that, when we apply a trigger pulse, so I am going to apply a negative trigger pulse to that second pin of that lower comparator. So here I am going to apply a negative trigger pulse of 1/3 VCC. It passes through the 1/3 VCC. Here the flip-flop sets to. So as I discussed, in the negative pulse, we are going to make our set condition. So you are going to make the flip-flop a set condition. So in that condition, my Q will be 1 and Q bar will be 0. So once the Q bar is low, it can't make that Q1 transistor to on, so it makes the capacitor to a short circuit. So that's the thing. Here the negative trigger is applied. It passes through the 1/3 VCC of that comparator of lower comparator, which makes the flip-flop to set condition, which is like a default Q is equal to 1 and Q bar is equal to 0, which makes that Q1 transistor to off condition, and the output will be in a high condition, which makes the capacitor to be a short circuit. So in that condition, the short circuit rises, the capacitor rises exponentially to a time with a time constant of RC. With a time constant RC. The third condition, after a time period, so okay, in that condition, after a time period T, the capacitor voltage is applied with a voltage which should be a greater than 2/3 VCC. So in that condition, your upper comparator gets reset condition. So in that condition, your flip-flop, your Q will become 0 and Q bar will become 1. So in this, Q bar is 1, which turns my Q1 transistor to on, and thereby discharging takes place. Capacitor discharges. So in this, the capacitor discharges suddenly, rapidly to ground potential. So this I will show it in the diagram. The thing, initially we have an additional pulse has no effect on output, that is your 0 volt and negative trigger pulse is applied. In that condition, your negative trigger pulse is applied, your lower comparator gets set. So in that condition, your Q will be 1 and your Q bar is 0. So this makes your Q1 transistor off and the output to be high. Okay. So in that condition, it makes your capacitor to a short circuit, that it grows exponentially based on the time constant RC. So once it reaches a proper threshold of 2/3 VCC, then it applies to the concept called 2/3 VCC. So then it will be greater than 2/3 VCC, then your upper comparator gets worked. So in this concept, your upper comparator is high, then your flip-flop will be in a reset condition. So in that reset condition, your Q will be 0 and Q bar will be 1. So you are making your Q bar as 1, it makes your Q1 transistor to on and your output to be high, output to be low. It's an inverse operation. Once you pass to that inverter power amplifier, you will be getting your output as low. So in that condition low, your capacitor, talking about the concept of capacitor, it discharges suddenly to the ground potential. So this is the time taken exponentially to that R and C based on this R and C component, and in the capacitor discharges immediately it comes to this point. So in this concept, the output drawn is like, so here that output will be high in case of this period to 2/3 VCC, and in this condition from 2/3 to the capacitor discharges. So here it suddenly drops to the 0 volt. So here your output becomes low condition. So this is the time interval for this calculation. You are going to calculate your time period C. So in this, the voltage across the capacitor in this Vc is nothing but Vcc into 1 minus e power minus t by Rc. So this is the expression for this starts from this value, it exponentially varies based on this RNC component. The capacitor voltage can be expressed as Vc equal to Vcc into 1 minus e power minus t by Rc. And the fourth condition, at t is equal to t, capital T, you can reach the maximum voltage of 2 by 3 Vcc. Then your capacitor voltage will be 2 by 3 Vcc. So in this we are going to equate this Vc and this Vc. So here 2 by 3 Vcc is equal to Vcc into 1 minus e power minus t by Rc. Then your Vcc factor gets cancelled. 2 by 3 is equal to 1 minus e power minus t by Rc. You can keep that exponential term to the one side, 1 minus 2 by 3. So you can write minus Rc is equal to 1 by 3. Then t by Rc is equal to ln of 1 by 3, removing that exponential factor. Then t is equal to Rc ln 1 by 3. So at time t is equal to capital T, I can replace this t as capital T as Tc Rc ln 1 by 3. So this ln of 1 by 3 is 1.1. So 1.1 Rc, that is seconds, the unit for this. So based on this, now your time interval t is depends on the RNC component and is independent of the supply voltage. So here, so up to this, initially a trigger pulse is applied, then it reaches the capacitor to get charges exponentially, and it reaches an upper threshold voltage. Then upper threshold voltage resets the flip-flop and suddenly it drops to the ground potential. So the time taken from the capacitor to charging and the discharging, we calculate this as the time period t. So the next condition, once when you apply the other trigger pulse, see here, when you apply the negative trigger pulse, then it reaches a 0 volt. At this condition, initially it's like a reset and it is applied a pulse, then it moves to the negative pulse and reaches 0 volt. So in that condition, once it's applied, your capacitor charges to this extent and it discharges. So here the time period will be like a half of, not like half of this, it's like these portions of this time period will be removed. So the output after some reset pulse is applied, it reaches that particular time period. Once a pulse is applied, reset pulse is applied, it immediately comes to the ground potential. It drastically drops to the ground potential. This is the concept of this monostable operation of this multi-vibrator. So there will be some drawbacks in this circuit. So when by mistriggering a positive pulse is triggered, so it may have changes in that circuit. So here even with the control pin, by using that capacitor, there may be some changes in that. So in case of that, to avoid that concept of that positive trigger pulse, we go for a modified monostable pulse. So in this modified monostable pulse, earlier we have used by erasing this is the concept. Fifth pin is connected to the first pin to be grounded, and your 7th and 6th pin is connected to R and C. So here 8th pin and 4th pin is connected to VCC. So now here we have an input, resistor, capacitor and the diode concept. So here, to avoid this positive pulse triggering, we are going to use that R and C combinations, the 10 kilo ohm and 0.001 microfarad to form a differentiator, and it uses the concept of diode. So this diode gets worked only in the case of that forward bias region, and it allows the maximum amplitude of 0.7 volt. So when you apply the positive pulse, it gives, it's like a 0.7 volt as that input amplitude of that diode as 0.7 volt. It limits the amplitude. So this is the circuit used for avoiding a positive pulse triggering in the monostable operation. So we go for a modified monostable operation with R and C acts as the differentiator and the diode concept becomes the forward bias. When the for positive edge trigger is applied, it becomes a forward bias which limits the amplitude of not more than a 0.7 volt.